Ladies and gentlemen, distinguished participants, colleagues and friends, hello and welcome to IPCMC 2020. My name is David Arditi. I am a professor at Illinois Institute of Technology in Chicago. I first want to thank the organizing committee for inviting me to deliver this keynote. My special thanks go to the co-chairs of the conference, Professors Birger, Polat and Günaydın, who over the years contributed a great deal to the advancement and growth of the CM profession. I will start by saying a few things about my school and my program. Illinois Institute of Technology is located in Chicago. It was established in 1893. It is basically a school of engineering, architecture, and sciences. All engineering programs are ABET accredited. We are a small school, 6,500 students compared to most American public universities. But the important thing about our school is that half of our students are graduate students and the other half are undergraduate students. I started the construction engineering and management program in 1981. The program has developed quite well. It is one of the most popular programs in the department and in the school at this time. My talk today is going to be related to energy-related issues in design, construction, and operation. First, a few observations. The very large proportion of the population of the world lives in urban areas. That means we live and work and play in buildings. 42% of the primary energy use and 39% of the global greenhouse gas emissions come from buildings. So I rest my case. This is the motivation for this series of studies that we performed in the last few years. My talk today is related to 5 small projects that we completed in the last year and a half. Some of these projects are indeed small, but a couple of them are quite large. We did this in the years 2019-2020, and I'm going to take them one by one, and I'm going to give you some information about each one quickly. The first project is an offshore wind farm in Lake Michigan. So if you look at the pie chart at the top, you will see that only 6% of the energy generated in the United States comes from wind energy. And if you look at the chart below, the blue line represents coal. You see a big decline in coal generated electricity, but a big increase, that's the green line, a big increase in electricity generated by using natural gas. Energy generated by nuclear power plants has remained very stable, and so has the hydropower system. If you look at wind energy, you will find that there have been increases over the years, starting in 2008, and by today it has reached about, well, by 2016 it has reached to 6%. In 2019 it has reached about 7%. However, wind energy can be produced by wind farms located on land or offshore. The number of wind farms located on land has increased quite a bit, but let's take a look at what is happening at wind farms located offshore. As you can see in this slide, the US shores have a power generation potential of more than 2,000 gigawatts. Now, this is a big number because it represents nearly double the nation's current electricity use. The first offshore farm was an experimental farm done in 2016, small plant, 30 megawatt capacity. Since then, between 2016 and 2019, 143 mostly smaller offshore wind projects have been developed in the United States. But there is still quite a bit of potential for offshore wind farms. So what is a turbine? A turbine has blades. The blades catch the wind. The wind turns the rotor, and the rotor transmits the movement to a generator that converts this into electricity. We have different types of offshore turbines. Some of them are fixed turbines. That means they sit at the bottom of the lake. They are appropriate in shallow waters where the foundation conditions are good. They are also quite popular. And we have floating turbines. Floating turbines are used in deeper places of the lake, and they are less popular than fixed turbines because they are a little bit more expensive and trickier to maintain than fixed turbines. Lake Michigan. Why Lake Michigan? Now here's a map of Lake Michigan. As you can see on the east side of Lake Michigan, we have the state of Michigan. Then at the bottom on the south, we have Indiana, and the southwest, we have Illinois, and then Wisconsin. 4 states flank Lake Michigan. Lake Michigan is a very big lake. It is part of the Great Lakes system. There are 5 big lakes between United States and Canada, and these lakes constitute the biggest body of sweet water in the world. They are connected to each other, and also these lakes are connected to the Atlantic Ocean, and there is quite a bit of freight that is transported through these lakes. Now, why locate wind farms in Lake Michigan? Number one, 2 of the states, Indiana and Wisconsin, have a deficit in energy production. The amount of electricity they produce is not enough for their state. They have to buy from other states. The state of Illinois is mostly a nuclear power state. That means over 50% of the electricity produced in Illinois comes from nuclear power stations. But 2 of them are going to close in about 10 years' time, which means that there will be a deficit in the state of Illinois also. So we will need new electricity sources. And finally, the city of Chicago is a very progressive city, and it has committed to using clean power in its public buildings by the year 2025. Finally, Lake Michigan is a very windy lake. There is a lot of wind. Predominant winds come from the northwest, and they flow towards the southeast. And there are no mountain ranges anywhere in between. The Lake Michigan catches a lot of wind, and so does Chicago, by the way. Chicago is also known as the Windy City. Now, what are the factors that affect the location of a wind farm in Lake Michigan or in any body of water? We have wind speed. This map you see here shows the wind map of in Lake Michigan. The dark red shows the places that get a lot of wind, 8.3 to 8.8 meters per second. The next factor is bathymetry. Bathymetry is the study of the depth of the lake. Some places are deeper than the others. Coastal sections are shallow, and the dark blue areas here that you can see in the middle of the lake are very deep. We're talking here 250, 275 meters. The next item. This map shows the soil composition. As you can see, all the shores have the blue color. Blue color means sand, except for Chicago. I don't know, for some reason, Chicago is not blue, even though I live by the lake. And when I look out of my window, I see a nice sandy beach. So I'm not quite sure why in this map it's not blue. In any case, silty and clay areas are in the deeper sections of the lake. Lake Michigan, there is quite a bit of maritime traffic. As I mentioned earlier, there is traffic coming from the Atlantic Ocean and through the Great Lakes. And we don't want to place a wind farm in the middle of the route of one of these nautical systems. Then we have the grid connections. You know, we are producing electricity, and this electricity is going to be sent to the grid, which means that the closer you are to the grid, the better it is. It is an advantage. And finally, we have nautical ports. We need the ports because we're going to use the ports to transport the material to build the farms and then to maintain the farms over the years. Given these 2, 4, 6 factors, we looked at the most appropriate locations for each type of wind turbine. We did this for monopile foundations, for tripod foundations, for jacket foundations, for gravity-based foundations, and for floating turbines. At the end of the day, we found that the east side of the lake, sort of midway between the north and south ends, is the place to place monopile foundations and gravity-based foundations. A little bit more south of that, we found that it is best for tripod foundations and jacket foundations. As far as floating wind farms are concerned, the best way appears to be in the middle of the lake, a little bit north, and where the water is deepest and where the wind is strongest. Are they going to be built in these locations? I don't know. We'll have to wait and see how this turns out to be. All right, the next project is the economic feasibility of a transition to a battery electric bus fleet in public transit. Now, public transit is essential in any densely populated area. In any metropolitan area, you need to have public transit. And the public transit we have in the US and especially in Chicago is very efficient, and unfortunately it is also very outdated and underfunded. Outdated it is because it is old and it needs a lot of renovation, and underfunded means because of budgetary reasons they have not been updated, and this is a chronic problem. Therefore, we need to do things a little more efficiently. The question therefore is, should we use electric buses? And by electric buses, I don't mean buses that take the electricity as it goes along from, from cables at the top or lines at the bottom, but we're talking here battery electric buses. So we did this with the Chicago Transit Authority. We did the cost predictions and we formulated a model to produce projections for the future. So CTA, the Chicago Transit Authority, is the second largest public transit agency in the US after New York. It carries a lot of people and it has very many bus routes, and those who have lived in Chicago will know that this system works pretty well. They have close to 2,000 buses, 1859 to be precise. Many of them, the large majority of them, diesel engines, some hybrids, and a couple of experimental electric buses. We first formulated the model by performing data projection and costs, and the costs we didn't include all costs, but we included vehicle purchase, fuel, maintenance, and overhead. The data we used in our model came from very many sources, some of them national, some of them state sources, the state of Illinois and other states. And of course, we made assumptions. As you know, whenever you make a model, you have to make assumptions. The vehicles have a life of 14 to 15 years. The vehicle undergo a major overhaul on the 7th year, right in the middle of their lives. The vehicles run 30,000 miles a year, and the fleet size and vehicle size are the same as what we have today. Our model involved a 24-year analysis, 2016 to 2040. We had 4 alternative strategies, the first one being the status quo. That is what we have today. The next one, only diesel buses. The next one, only hybrid buses. And finally, the last one, only battery electric buses. 3 scenarios were considered, with the diesel price being like today with some discount. And the second scenario was the diesel fuel's price goes down very low. And finally, last scenario, the diesel fuel price is very high. This is the graph we obtained from our model. This is a prediction between the years 2016 and 2040. And you will see that the gap between electric buses and the other alternatives is pretty big, which shows that electric buses are desirable. If we take this next scenario where the diesel fuel price is low, then in that case, you can see that the gap narrows down, which means that electric buses are still very desirable, but not as much as in the base scenario. And finally, if we have the high diesel price scenario, in this case, you will see that the gap is as large as it can be. In this case, there is no question that battery electric buses are much more desirable than any of the other alternatives. The conclusions state that battery electric buses are the most efficient solution to the problem. They are more desirable in any scenario. Number 2, hybrid buses can be efficient more or less as the present systems, but never as efficient as battery electric buses. And finally, if we shift to battery electric buses, the city of Chicago is going to save $200 to $400 million over 24 years. Therefore, the biggest conclusion of the study is let's switch to electric buses right away. The third project has to do with the district cooling system. This is particularly suitable in a large metropolis, and we investigate this to a certain extent. A district cooling system involves a plant, a cooling plant. The cooling plant is located close to a number of buildings. It produces chilled water that it pumps to these buildings. There is a heat exchanger in every building, and the buildings are going to be cooled in the summer using the cool water provided by the cooling plant. There are quite a few advantages of the district cooling system. First of all, the chillers in the plant are run at night. Why at night? Because the electricity rates are very cheap at night. The second thing is that because all the equipment is in the central plant, there is no equipment, or very little equipment, in the individual buildings. The individual buildings do away with the cooling towers and chillers and all the other equipment that they use. They only need heat exchangers that occupy very limited space. So there are quite a few advantages to using a district cooling system, but the problem is the district cooling system more economical or not? This is what we investigated in this study. As an example, we took the Chicago district cooling system. As you can see from this map, there are 5 central cooling stations, and that serve a total of 120 buildings in downtown Chicago. So this is the largest system in the nation. It is a very well-developed system and has been there for quite a few years. We calculated the cost of owning and operating cooling systems in each one of the 120 buildings in downtown Chicago. We calculated the installation cost of the constituent equipment, meaning the chillers, the cooling towers, the water tanks, etc. We calculated the replacement cost. Every now and then there will be a major overhaul. Certain equipment will have a limited life and they will be replaced by newer equipment. We calculated the repair cost over the years of all the equipment. We calculated the maintenance staff cost, that is labor cost to upkeep the entire system. We calculated the opportunity cost and the power cost. The total was around $1,235 million over 50 years. We also calculated the operating cost of the district cooling plant and the distribution of water from the district cooling plant to the individual buildings. So again, we calculated the installation cost of the various equipment. We calculated the replacement costs, the repair costs, the maintenance staff cost, the opportunity cost, and the power cost. The total was $1,112 million over 50 years. So the difference, as you can see in this slide, is $122 million over 50 years. That means a saving of about 10%, and this is the conclusion of this study. Project number 4 involved a life cycle analysis of the environmental impact of structural steel. Life cycle cost analysis evaluates the environmental impacts throughout the production, usage, and disposal of a product. We're not talking about life cycle costs. We're talking about life cycle cost analysis. Actually, we're looking into environmental impacts rather than costs. So in this study, we looked at the cycle life cycle of structural steel. You know, buildings are either made of reinforced concrete, timber, or steel. And especially tall and super tall buildings are constructed with steel components. So we looked at the entire life cycle of structural steel, starting with the scrapyard, where the steel is dumped. So you handle the material in the scrapyard, then you send it to a steel production facility that uses electric arc furnace technology for this purpose. For this research, we decided to use electric arc furnace because it is the most energy efficient system at this time. And then it is sent to the fabrication plant where the steel is formed, bent, punched, drilled, and welded together into components. Number 4, then it is sent to the construction site where the steel components are assembled on the construction site. So transportation is involved in between each one of these 4 stages. So the energy implications of all these 4 stages, including the transportation between the stages, have been investigated in this study. So the environmental impact criteria that we considered are carbon dioxide, carbon monoxide, nitrogen oxides, sulfur oxides, particulate matter, hydrocarbons, and volatile organic compounds. At the end of our study, we found the amount of pollutants in each phase, in each stage of the life cycle of steel production. You will note that in some cases there is no information in the row. For example, there is no information for baler. Balers are considered to be electric machines, and they do not produce any of these pollutants. So therefore, there is nothing to report here. Same thing with bending and punching. These are mostly electric machines that do not involve internal combustion engines, and therefore none of these pollutants are emitted. So the sum of these pollutants are given here at the bottom. We did this, so you're going to ask, what about the transportation? Transportation between the scrapyard and the production area, the production and the fabrication and erection. Where are the transportation? We also calculated the emission of pollutants for different modes of transportation, in this case by trucks, by train, and by ship. The conclusion of this study is that we now know the environmental impact of producing steel, starting from the handling of the scrap in the scrapyard until the erection on the construction site, including transportation. So if we want to reduce this impact on the environment, we know exactly what to do in what stage of the life cycle. This is particularly important for tall buildings and super tall buildings that use predominantly steel components. The final project took more than a year and a half to complete. It has to do with multi-objective optimization of LEED scores and life cycle costs. As we know, LEED is used extensively in very many countries. 96,000 projects were certified in 167 countries so far. And LEED does reduce the negative environmental impacts, but also it is very expensive to implement. And this is an impediment for many construction owners. So we need to have some sort of an approach that balances the LEED certification against the cost of producing these buildings. So the objective of the study involves examining all LEED credits. We used version 4, building design and construction, by including the associated costs, energy implication, environmental impacts into a big database, and then use multi-objective optimization to reconcile the life cycle costs and sustainability. First, we looked into multi-objective optimization techniques. As you see, there is a long list here. We looked at the advantages and disadvantages, the practicalities involved in each one of these, and we zeroed in on the highlighted non-denominated sorting genetic algorithm 2. NSGA2 is a commonly used multi-objective optimization techniques and very efficient, and it proved to be very efficient in our study also. I'm not going to bore you with many equations and details, but I'm just going to say that we formulated two objective functions. Objective function number 1 is the maximization of the LEED score. In other words, an owner specifies that he or she wants to have a silver certification. So this function is going to determine how many points in each credit one should score in order to reach the minimum credits required to get silver certification. Objective function number 2 is the minimization of the life cycle cost. The idea is not just to maximize the score obtained in LEED, but also to get the smallest, the lowest life cycle cost. Of course, there are very many constraints in the shape of prerequisites and in the shape of little credits. As you can see, the total of number of constraints in our study was 46. These are the prerequisites and the credits involved in the 9 categories of LEED. And I'm not going to put all 46 of these on the screen. We don't have the time for that, but I will give you one example. The example I picked is the heat island reduction. It says X sub SS superscript 5. That means this is the sustainable site category, and this is the 5th credit of the sustainable site category. This score can be 0, 1, or 2, depending on these relationships, and subject to these constraints. So the meaning of all these variables in the preceding equation are given in this slide. The optimized solution is plotted on the screen. As you can see, if you want a certified building, you need at least 40 points. This is going to cost you $28 million, and it is this point here. If you want the silver certification, that will require at least 50 points, and this is going to cost you $29 million, and this is this point here. And finally, if you want gold certification, that will require 60 points. It is going to cost you more expensive. The life cycle cost is going to be 30 million and change, and this is this point here. The optimization system also gives a table like this, which tells you exactly how many points you should get in which credit, in which category. The sum of these credits, by the way, in this table equals 40 for a certified category. The conclusion of the study can be summarized as follows. The LEED process is very complex. There are very many credits that are interrelated, and there are very many credits that appear in many of the categories. So it is difficult for designers to make decisions as to which, how many points to get in from which credit. If one has access to a system like the one we propose in this study, we think that designers are going to have an easy time making decisions and achieving their objectives. Finally, a few remarks about the 5 studies I reported to you today. The world is getting urbanized rapidly, which means we have lots of buildings. Buildings do consume a lot of energy, and buildings do have a lot of negative environmental impacts. Any research done in energy-related issues, environment-related issues, is worthwhile. The 5 studies that I reported to you today do not even scratch the surface of what is being done today in terms of energy research and environmental research. But nevertheless, these are examples, I think good examples, done in a short period of time that show that these are worthwhile studies. Thank you for your attention, and enjoy the conference.